In this lecture, we will learn why do some people need glasses, the structure of the human eye and the power of accommodation that it has, and what are the defects of the eye, namely myopia, hypermetropia, and presbyopia, how they are corrected, and what is the power of the lens required for correcting these different defects. Welcome to the portals of real learning. Listen carefully and completely. So we come to the last chapter of optics, which is a very interesting chapter called Human Eye and Colorful World, where we are going to learn how the human eye works, how the defects of eye can be corrected by corrective lenses, how the prism can do what is called dispersion, breaking up white light into its constituent colors, atmospheric refraction, and scattering of light. In this session, we'll talk about the human eye and the defects and their correction. The human eye has been a subject of much poetry and romance. Ben Jonson wrote, "Drink to me with thine eyes, and I will pledge with mine." Then you have Bollywood songs, Ye Kali Kali Aankhein, Ye Gore Gore Gaal, or जीवन से भरी तेरी आंखें मजबूर करें जीने के लिए. So all that poetry is fine, and what you see on the outside is only this much, but the eye structure is a lot more lies on the inside, and outside what is visible is only this much. Let us look at the essential components of the eye. You have a lens, it is a convex lens. You have a screen, that screen is the retina. You have an aperture, so light comes in, gets refracted, and the image is formed on the screen. It is a real image because it is formed on the screen, it is inverted. So if an object is like this, the actual image created is like this. But then the retina then sends electrical signals via the optic nerve to the brain, and the brain then interprets the information. What is the object? How big is it? How far is it? What is the color? What is the brightness? Is it moving, not moving? All that the brain is able to decipher. Now, this aperture can be controlled by this iris. If there is less light coming in, then the iris will open up to allow more light to fall in. If it is very bright outside, then the iris will close to make the aperture smaller to allow less light. So all that is automatic. You don't have to do anything. The iris takes care of itself. Then there's a transparent outer layer called the cornea. There is a transparent part here which is a fluid called aqueous humor. In this anterior chamber it is there. Behind the lens also there is a transparent fluid called vitreous humor, and that is called the vitreous chamber. And the lens is convex, but it is not made of glass, it is made of organic matter whose shape can be changed. And the shape is changed by these muscles called the ciliary muscles, and they perform a very important role. So, let us see how this works. First of all, the image distance is fixed. For all types of objects, the image distance is fixed. That is the distance between the lens and the screen. If the eye is like this, approximately like this, and this is the lens, and this is the screen, so this is the image distance that is fixed. That is 2.5 centimeter. But we want to view different types of objects. Some are very close, some are very far. So U is variable, but V is fixed. And if you apply the lens formula, this V is fixed. This second term is variable. And in order to satisfy this equation, the right side should also be variable. That means the focal length should be varied. For a normal eye, the closest object that we can see is 25 centimeter or 10 inches, and that is called the near point of the eye. For a normal eye, it is 25 centimeter. If the object is any closer, we can't see it. If we take a book and keep it like this, nearly touching our nose, then we can't read it. We have to keep it at some distance, right? 25 centimeter at least. That is a near point. Then the far point is infinity. We can see stars, for example. So for a normal eye, the near point is 25 centimeter and the far point is infinity. Now the object can be anywhere from 25 centimeter to infinity. The focal length should be varied, and that is varied by altering the curvature of the lens, and that is done by the ciliary muscles. And this power is called the power of accommodation. And this happens automatically. You don't have to instruct the ciliary muscles to do anything. Right now, you're looking at the book, then you look at the tree. The ciliary muscles automatically adjust the focal length of the lens. Curvature decides the focal length. If there's a large focal length for a parallel beam of light, it will create an image at the focal point. The focal length is large, and look at the curvature of the lens. But if it is small focal length, then the curvature should be this. The radius of curvature of both the surfaces has an important bearing on the focal length. This radius is larger. The radius of curvature, if I consider both of them to have the same radius of curvature, that is larger, and here the radius is smaller. To make the radius of curvature smaller, the ciliary muscles have to compress the lens, therefore they are under tension. If you're looking at a very far away object, then your eyes are not strained because the ciliary muscles are not strained. But when you're reading a book, you can't keep reading it for hours and hours together. You need to give rest to your eyes because the ciliary muscles are strained. So here in this picture, for a far object, the lens is like this, the ciliary muscles are relaxed. The image has to be created at the retina, there is no compromise on that. But if it is a near object, the lens shape must change in order to create the image at this point. So that is called the power of accommodation, and the function is performed by the ciliary muscles. Two eyes are better than one. Human beings, animals, birds, all of them have two eyes. There are two reasons for that. One is we get a wider field of view. With one eye, we'll get a field of view of 150 degrees. So like you're looking straight at something, but you have an idea from the corner of your eye what is going on here, what is going on here. And that angle is 150 degrees with one eye. But with two eyes, that angle becomes nearly 180 degrees. You can make out what is happening here without turning your eye that side. You can make out. So wider field of view is one. And second, the two eyes are positioned at slight separation. So you're looking at object from two slightly different angles that gives you a perception of depth or perception of the stereoscopic content. In this picture, how far is the second car from the first one? How wide is the road? All that perception of depth we get because of two eyes. Now let's talk of the defect. One is called myopia. Myopia means nearsightedness. That means you can see close by objects, but you can't see far away objects. Those objects are blurred. And this typically happens during the growing up years. You'll find that some children in the classroom may say that I can't read what is written on the blackboard. The blackboard is not that far. It is 20 feet, let's say, at most. But yet he can't see the letters written on the blackboard. He can read a book. He is nearsighted, but far away objects he can't see. That means the far point is impaired. For a normal eye, it is infinity, but for this person, it is impaired. That is called myopia. What happens is that suppose an object is very far, let's say infinity, then after all the refraction, the image is being created somewhere in the middle, not on the retina. So whatever the retina receives is all a blurred image. The farthest that you can see is this. So this distance is the far point of this particular person, which is less than infinity. Any farther, the image doesn't form on the retina. This happens when the eyeball grows faster than the other things, and therefore it typically happens during the growing up years. This is not a disease, it's a defect which can be easily corrected by a lens. What do we have to do here? What we have to do is, this is the farthest that he can see, right? So if any object is farther than this point, it should be brought closer. Not physically, not physically. It should be brought closer, either here or somewhere in this region. This region for him is good, right? So we have to basically create, here's the object, we have to create an image in this region, either here or here or here or here or anywhere, up till, let us say, the near point, which is from here to here is 25 centimeter. We have to create an image of a faraway object at a distance less than the far point. So what do we do? Talking of an object at infinity, the rays are coming parallel. We put a concave lens in its path. So instead of going in the original direction, this is a diverging lens, so it diverges a little bit, and therefore the image is now created properly on the retina. So object is at infinity. When you produce these rays backwards, the image is created. So for the farthest possible object, the image is created at the far point. You can see that. For any other object, let us say the object is here, not at infinity, then if you look at this picture that we have seen earlier, for an object not at infinity, the image is formed between the focal point and the optical center. This distance right now is the focal length of this lens. For a very far away object, the image is created at the focal point. If it is any closer, the image will be created between this F focal point and the optical center. So somewhere here or here or here, wherever. So therefore we are fine. So we can design the lens, that is the focal length of the lens, based on his far point. That is basically the U is minus infinity for this lens, and the V is minus the far point. Far point is some number, say 100 centimeter. V is minus. So you have the U and the V. From the lens formula, you can calculate the focal length and decide on this lens accordingly. That is myopia, nearsightedness. Another defect is called hypermetropia, which is farsightedness. For this person, he can't read a book. He's far-sighted. He can see far away things, but he can't see nearby things. For him, the near point is impaired. For a normal person, the near point is 25 centimeter. For him, it is impaired. It becomes larger than 25. The closest that he can say is this. The closest that he can say is this. So such a person, if he wants to read a book, he can't read it like this. He has to keep it far away. But then he can read it, but then the letters become smaller, so it's a big problem for him. If he keeps the book this way, he can't see the letters. If he keeps them far away, he can see the letters, but the letters appear smaller. So it's a big problem then. So what is the solution for this? You see, the problem is, this is the near point for him. From here to here is the near point for this particular person. If the object is any closer, then the image is being formed somewhere behind, and retina will create a blurred image therefore. So what is the solution? If the object is here, need to drive the object farther, not drive the object farther physically, but create an image farther somewhere beyond this, either here or in this region, because he doesn't have a problem with faraway objects. He can see stars, he can see very, very far away objects. So the solution here would be a converging lens. This is his near point. This is the object that he wants to see. So if I take the closest object that he wants to see will be like a normal person, 25 centimeter. Any normal person can see only up to 25 centimeters. So if I consider an object at 25 centimeter from the lens of the eye, then the image must be created exactly at the near point of the person. So we have the near point available with us, that is a V. So V is minus the near point, it's a negative quantity. And the U is minus 25 centimeter. Accordingly, we can calculate the focal length of this convex lens. Now, suppose the object is farther, then where will the image be created? The image will be created somewhere here. If this is O dash now, I dash will be here. He doesn't have a problem with this because beyond this region, he is perfectly fine. He is okay with that. And you can see this is how an image is created by a convex lens when the object is between the focal point and the optical center. The image is created here. Now, how do I say that if the object is moving farther away, then the image will also go farther away? How do I say that? Well, think of the lens formula. 1 by V minus 1 by U equal to 1 by F. So 1 by V is equal to 1 by U plus 1 by F, right? U is a negative quantity. The whole thing is a negative quantity. F is a positive quantity. But U is less than F in terms of magnitude. The object is placed between F and O. So U, magnitude-wise, is less than F. Therefore, it is overall a negative quantity. 1 by V is overall a negative quantity. Now, if we take the object farther away, then the magnitude of U is increasing, but it's still less than the focal length. The magnitude of U is increasing. So this magnitude increases. Therefore, this term becomes less negative. And the overall 1 by V becomes less negative. Therefore, since it is a reciprocal of V, V becomes more negative. More negative means going farther. And he doesn't have a problem with that. What about the power of this lens? That will be positive because power of a lens has the same sign as the focal length. For a convex lens, the focal length is positive. And if you go back to the myopia, the power of that will be negative because this is a concave lens. So if you are using spectacles, I'm sure that the power of your lens is negative because at your age, you would be having myopia only, not hypermetropia. Now, why does this happen actually that the eye is not able to focus it on the retina? The image is created far behind because the ciliary muscles have lost their ability to compress the thing, and that happens by age. So presbyopia is basically hypermetropia due to aging. With age, the ciliary muscles weaken, therefore the power of accommodation reduces and the near point increases because the ciliary muscles are not strong enough now to compress the lens of the eye. So anybody who is more than 40 years of age will have presbyopia. 95% people will have presbyopia because with age, the ciliary muscles are getting weak. But this can happen without aging also. Hypermetropia can happen without aging also. So sometimes, in fact, a person can have both myopia as well as hypermetropia. That means the near point is impaired and the far point is also impaired. Then he will use a spectacle like this. If he wants to see a distant object, he will see from this part of the lens. And if he wants to read a book, then he will use this part like this. And seeing from here, if he wants to read a book like this. And if he wants to see a movie, then he sees on this side. So these are called bifocal lenses. So those were the defects of the eye and their correction. They are defects, they are not diseases. So in the next session, we are going to talk about prism and this breaking up of white light into its constituent colors, which is called dispersion. That will be the subject of the next session.